Okay, ma'am, will start. Good afternoon, everyone, and welcome to the next second day in this two-day workshop which I have lined up, a hands-on workshop on citizen science project and robotics. Oh, yesterday we have discussed various citizen science opportunity in which anyone with the basic requirement can contribute if they wanted to pursue in this direction. And today we'll be talking about little complex things about the robotic telescopes and how the data and things can be taken and how to pursue. And with this workshop, Dr. Priya Hasan, as already you all met yesterday online, and you shared your things, your queries and doubts. And today also Dr. Priya Hassan from Maulana Azad National Urdu University. She's an assistant professor there and very actively involved in various citizen science projects and also in making astronomy and space science studies available and accessible to all across age group of country. So, Dr. Priya Hassan, on behalf of Planetarium, Prime Minister Museum and Library, I again welcome you for the second session. uh, and we can start it today. And also because today is a very special day, today we have also celebrated the 50th glorious years of Aryabhat, India's first indigenous satellite, and we did several programs to commemorate this celebration. So it's important to take the name because this was the India's if we talk about the leap in space sector. So with this note, I think we can start the session, ma'am. Over to you.
Yeah, thanks a lot. Thanks a lot, Prerna. Thanks and welcome everyone to today's session. I just wanted to check, Prerna, is YouTube working fine? Because when
Yes,
it's on YouTube,
yes, yes.
because when I click the link, somehow I get it. It says it's been removed or re-uploaded or something like that. Has the link changed? It's there.
Yes, there it's coming, ma'am. It's live.
Okay, very good. So thank you everyone, and thank you for coming for attending today. Uh, I'll mute you also. Yeah. So I've muted you, Prerna. Yeah. Thanks a lot. And welcome to our second day. Today is yet another thing, and this is also something which I'm very enthusiastic about. This is about observations with robotic telescopes. Now, I'll tell you why robotic telescopes are interesting and important. And I'll just share my screen. And please let me know. You can see my screen fine.
Yes, ma'am, it's coming. You can make it full screen.
Yeah. Yeah, so there are various sets of robotic telescopes, and I'll be talking about a particular set of robotics, which is called the LCO or the Las Cumbres Observatory. Okay, now specifically for countries like India and for many places, the advantage of these using these robotic telescopes is that otherwise, there are only select places which have telescopes, and often we do not have access to those telescopes, right? So the whole fun of observing is when you can actually plan your observations, decide what do you want to observe, why do you want to observe, where do you want to observe, right? And accordingly, you can plan your observations. So advantage with robotic telescopes is I have membership for these LCO robotic telescopes. They have a Global Sky Partners program. And therefore, if there's anybody of you who wants to actually use the telescopes, do get in touch with me and I will give you the login, etc. And you can actually do it. I'm not giving it to everyone because even yesterday we had like almost 300 participants and I have only 100 hours. So I don't have enough of time. But otherwise, if there are a few of you who want to actually observe, please get in touch with me. You remember my email. I showed it to you yesterday, priyahasan@gmail.com. You can write to me and I will give you the necessary login, etc. So if you want to observe, you can do it. Okay, now the concept behind the Las Cumbres Observatory is a very beautiful concept. It's a very nice, novel concept. So let's actually just talk about it. You basically have 25 telescopes, which are at 7 sites. You can see the 7 sites all around the world, working as a single instrument, okay? So I'll tell you what the concept is about. So I'm going to actually, I hope I can cover these things. I'll talk a little about what is LCO, what are star clusters, what's an HR diagram, what is photometry, how do we standardize. So you see I have a very ambitious line of things which I plan to do. So let's hope I can manage it. And what we will do is that if you cannot all run it here today, you can actually, we can give you some time to run it, right, Prerna? And then we can have a follow-up session later, because in this 2 hours, I don't know how much I can cover of this, right? So let's see how it goes. So first of all, let's come up with the first question. What exactly is LCO? So LCO is the Las Cumbres Observatory, which is basically 25 telescopes at 7 different sites. So you have 1, 2, 3, 4, 5, 6. So actually there are more sites, this thing, around the world, working as a this thing. Now, what is the basic concept behind it? So it's run by a non-profit private operating foundation, which was directed by a person called Wayne Rosing in September 2005. The main office is in California. And what they basically did is that they placed telescopes all over the world in the northern as well as the southern hemisphere, right? So one reason of doing this is that you have accessibility to various sites all over the world. And this is very important because supposing there is a transient event, right? There's an event which you want to actually observe, right? Then in that case, there could be a period when it's, say, observable, for example, in America, and then later on in Africa, and then in India and Australia, or the other way around. It would actually work like this, that you'll see it first in Australia, and then, because as the Earth rotates, it will come like that. So what happens is, depending upon the position of the object, you can actually track this object through various different observatories all over the world, right? And in that way, you can actually catch these transient observatories. So in the southern hemisphere, you basically have the Cerro Tololo Observatory. These are already, these are already good professional astronomy observatory sites, right? So otherwise, a big effort is taken in what we call site selection, in actually selecting the site. So here I have 7 over here, or whatever. Okay. So what happens is you're actually looking at good sites where there are already existing observatories. So what the concept is that Las Cumbres uses these sites to actually install their telescope, which in principle is robotic, right? So it does not require daily maintenance. These robotic telescopes do not require daily maintenance. They anyway work, right? So there are various telescopes you can see. This is in Chile or in South Africa and Australia, in Texas and Hawaii and Canary Islands. So it's there at various locations. And because it's already at an observatory site, so it kind of gets taken care of, but we do not need somebody to be actually handling the telescope on a daily basis, right? So these are robotic telescopes. So that means that the telescope can make observations without a hands-on or human control. We'll see that today itself, when we are actually putting our data, we are actually controlling the telescope in that way. So it's basically automated, computer controlled. And what happens, it basically runs, the basis of it is what is called a scheduler, right? So for example, I give a certain object, and this, the scheduler checks out that this object, where is it observable in compared to all the sites, right? Which we have in the northern and southern hemisphere and at all different latitudes. So it actually chooses which is the good site where you can actually observe it. And then based on that, the scheduler actually allots an observing plan to all these telescopes based on the requests which it gets, and it actually observes it in that way. So, and then what happens is the person who actually asks for the observation, you finally receive an email which tells you your data has been collected and you can actually download it from wherever, from the website, from their website, right? So that's how it basically works. Now it's unique for the simple reason that if you look over here, 1 minute, I'll just try to move this thing. So you can see you have the different sites over here. 1, 2, 3, 4, 5, 6, 7. Yeah, perfect. So now you can see 7 perfect sites over here. And so like you see, there's a nice global distribution of telescopes. Like I told you, one of the major reasons is to, for example, observe transient phenomena. In today's times, now what has actually happened, there was a time when people were basically just studying the sky, right? And we had lots of sky surveys where they basically tried to observe the sky in lots of detail. But now the thing is that we know a lot of sources in the sky are actually variable, right? And therefore now what is being done more in astronomy is to basically look for variable sources. You're looking for transient sources. So it's not that you are observing the sky only once, you are observing it repeatedly to look for changes. So we don't have the time to talk today, but there's a very big telescope which is coming up, which is called the Vera Rubin telescope. It's an 8-meter telescope, and it's going to basically scan the sky all the way. So every 3 days, it will repeat the scan of the sky, and it's basically for the idea of looking for transients. Because in present day astronomy, there's a lot of importance being given to transient astronomy that is coming from sources which vary with time. Okay. So what happens is if I have a transient source, I can actually start observing it, say from Australia, then I look for a bit over here, and I move gradually. This is Canary Islands, and then South Africa, and I gradually move and I observe it at these various locations. The other thing of these things is that there's dynamic observation scheduling. So for example, I give the request to the scheduler for an observation. The scheduler actually updates the network every 5 minutes. So it actually looks for new requests, and actually based on that, it decides whether it requires to observe some other object, right? Depending upon the request which comes. So for example, if I have what is called a target of opportunity, suddenly there's a source which is very important and very bright, which needs to be observed, and you put it onto the LCO scheduler, it will actually give it a priority and observe it, right? Now, the other important thing is that throughout the network, all these telescopes, they have exactly the same instrumentation, okay? Because what happens that often, if you have a difference in instrumentation, then when you're trying to standardize magnitudes, etc., you may have problems because if all your telescopes are of different types, they may have different characteristics. Some of them may be more sensitive in the red region or in the blue region, or they may behave differently. And therefore, it's always safest to have the same kind of thing. So all these telescopes have uniform instrumentation. Everything is exactly the same in all of them. And then, like I told you, it's fully robotic operation. So once it's given, things are done. And you have a rapid delivery of data. You can see that if we actually put in an observation, there are chances that today itself, while the session is on, I may get the data itself. So I'm going to try that out. Let's see if we get the data itself while we are doing the observations. If not, we will get it from the archive. But within minutes, often within minutes, it actually manages to give you the data, right? So that also makes it a very useful thing that you have this like that. Okay. Now, the largest telescopes these people have are 2-meter telescopes, but it doesn't come in this thing. We do not get access to the 2-meter telescopes, but these are, in Hawaii, there's an observatory, as well as in the Siding Spring Observatory, this is in Australia. So you have these 2-meter telescopes at 2 locations. And then you also have 13 1-meter telescopes, with two more will be added to the Ali Observatory in China. So you have all these 1-meter telescopes. And but they also do not come under the Global Sky program. So I will not be talking about these. Let's just know about the existence of these. But from the archive, I'll show you the data archive, where you can see the data that has been observed with these telescopes. You can actually take the data from the data archive of objects from these telescopes. Okay. Now, what is the instrumentation? The instrumentation basically for the 1-meter telescope is a camera, and it's a spectrograph, which has a resolution of 45,000. That's there on the 1-meter telescope. Okay. But the 0.4-meter telescopes, which are the smaller ones, these ones basically have an imaging camera, which is as big. This is the camera which is there on it. Okay. So the 40 centimeters, we are going to basically concentrate on the 40 centimeters. They have a camera called the S-Big camera. This is a field of view of 20 to 30 arc minutes, 12 filters, and we'll actually look at that in more detail now. So this is the instrumentation. We are basically going to talk about the 40 centimeter telescopes. So the typical site, for example, this is one of the sample sites. This is a site where you have 3 1-meter telescopes, and you have these up to 6.4-meter telescopes, which are at a different location and kept in this great site. Okay. Now, what are the sources LCO uses? It uses this astronomy event observatory network, which basically, and the target and observation manager, as well as the LCO Mars. Okay. It makes alerts. So this basically looks for alerts. In astronomy, there are alerts which are given out when you suddenly have a variable source which is worth observing, right? So let's repeat this. You have these 2 ones in Tibet, in China. You have the ones in Australia. You can see this, the 2-meter and the 1-meter telescopes. You have it in Israel. This is the WISE Observatory. There is in Tenerife, Canary Islands. This is South Africa. And you have Chile, Hawaii, and Texas, right? So we have a 1, 2, 3, 6, 7. Okay, we had, okay. So you have, these are all the telescopes which are there on the various sites. So what are they useful for, these telescopes? So one thing is it's for excellence in science, and what we are concentrating about is using it for education, right? So let's see a little bit about the science of what is the LCO been used for. So there was actually an LCO graduate student who actually used these telescopes to find the discovery of a gas bubble orbiting Sagittarius A star. This is the star which is very close to the galactic center, the Milky Way galactic center, and he actually discovered a gas bubble which was orbiting the black hole, this thing. It's also used a lot for time domain astronomy. For example, the first kilonova, if you've heard about the kilonova, the first kilonova was actually discovered using Las Cumbres Observatory, because what happens is the alert came from the Fermi satellite. The Fermi satellite is a gamma ray satellite, and it actually observed this kilonova. But the problem is what we call about location, right? You want to, basically the idea is we want to find an optical counterpart for the source, right? For a kilonova. So the kilonova source is observed, was basically observed in gamma rays, right? But what you have is the localization of the source, right? Is the tricky job. So how do you actually localize the source? So initially when you had the source, you can see that the Fermi satellite detects it and the red bands are showing you that, right? But you have such a large range, you don't know where your source is. But then when the LIGO and Virgo detectors, they triangulated the data, they actually found a smaller region where you can this thing. And then since LCO can actually search quite comfortably for it actually searched for it and actually found, here is the optical counterpart. This is in the galaxy NGC 4993. It actually found an optical counterpart for the kilonova, right? So this was actually found using the Las Cumbres Observatory. So this was actually, the alert was in 2017. There was an alert of a neutron star merger from the LIGO Gravitational Wave Observatory. And they had a larger region, search area was a larger region. So they searched about an area of 30 square degrees, right? A very large area of 30 square degrees. And then tried to search for the possible counterpart. So the ELSO telescopes in Chile, they saw the kilonova, and as it rotated, they actually re-observed it from the other sites at Australia, South Africa, etc., obtained the spectrum and verified, and this is the kilonova, which you can see, this bright object on top of that galaxy, right? So it could be used to actually identify. LCO is also used to detect and study exoplanets using 3 methods. You can use using microlensing, transit, and radial velocity techniques to actually look for it using the LCO, right? LCO can also be used, it has been used to look for super Earths. So they've actually got a specific instrument, and this is an instrument which is which could be actually used to look for exoplanets. So there is also an exoplanet watch program. Yesterday also, I think I spoke a little bit about it. It's a citizen science project. It basically looks for transiting exoplanets. And if you actually identify them, you can very comfortably, we don't have the time today, but one can actually use the, what you basically want is you want light curves, right? You want light curves, which is the difference in brightness of a source, right? Because if there's an exoplanet, then the brightness from the star will slightly dip, okay, because of the exoplanet. And one can use Las Cumbres Observatory. The telescope is small. You may say 40 centimeters is small. But the thing is, number one, the thing is that all these telescopes are at very good sites, okay? All of them are at sites of operational astronomical observatories. So they are already established good sites. And then what happens is that if the exoplanet, if the star is bright enough, you may have a good enough dip and you can actually observe it. So even the 40 centimeter telescope proves very worthwhile in doing that. And these, like I mentioned yesterday, these are used as indicators for us to identify candidates for these other, for objects which, for example, James Webb or something else may actually observe. Hello? Good afternoon. अच्छा बाद में, okay, 1 minute. So sorry, I'm sorry. I picked that up because I thought maybe it's Prerna. Okay. So I hope you'll have heard about the DART asteroid impact. So this was a very ambitious mission by NASA, that there was this asteroid. Okay, we know that there's always, yesterday we spoke about the fear of asteroids impacting the Earth, right? So NASA was already onto a program of checking of how can we actually mitigate such a thing, right? Now, one of the ways in which you can mitigate such a thing is basically by, you actually, they actually sent a spacecraft called DART, and it impacted an asteroid, okay? And when it impacted the asteroid, it was, the thing is, this asteroid was made up of a binary, okay, Dimorphos and Didymos. Okay, so what happened, it was very easy to actually check the change in orbit of this asteroid, okay, because it was part of a binary system. And therefore, when this impact was done, then it was observed using LCO telescopes. There was also the Atlas telescope, which was actually used to look at the impact. So you can see after the impact, you have all this dust coming out. And basically, it was used to actually check. This test was basically done by NASA, which was called the NASA Double Asteroid Redirection Test. This was a test in connection with what we were talking about yesterday. In the case of an asteroid impact, if you want to save the Earth from an asteroid impact, they try to check that supposing if we hit it with you hit it with a spacecraft, right? You don't need to bombard it. All if you hit it, if you can just change the trajectory, right? So supposing this asteroid is on a head-on Earth collision, but you hit it and you kind of change the trajectory, then as long as the asteroid it misses the Earth and goes somewhere else, it's good enough, right? So the DART mission was basically a test done by NASA to actually hit this binary system, which was made up of Dimorphos and Didymos, these two asteroids, okay? And they basically checked what was the change in orbit which they could produce by impacting it with this spacecraft, so that they can actually check, can planetary defense, can we do something in terms of defense? And what they found is that it was very, very successful. That means in principle, if we know it early enough, then in principle, it is possible to kind of change the path, change the course of an asteroid by basically getting that hit and moving it like that. And LCO telescopes was very effective in getting this, because for this you needed cover of this thing happening over time, right? And that could be what LCO could provide, and that's what they've done. There are also a lot of educational and citizen science projects which are done using LCO. And there is what is called the Global Sky Partners. We are part of the Global Sky Partners, Shrishti Astronomy. And therefore, we plan different things, educational things, which we can do with the LCO telescopes. So in Shrishti Astronomy, what we do is we are using it for educational purposes to basically show students how to actually observe stars, variability, etc., even exoplanets and things like that, and use our time to observe and get data, right? So Shrishti is what we run. I won't go into more details because that would be self-promotion, but essentially it's there, and you can actually check up our website, shrishtiastro.com, and see what are the kind of work we do. So we've conducted many workshops already about this, and most of it is available on my YouTube channel, where you'll find much more details and you can actually do it. So you can see that there are many science cases and many things that can be done using the LCO, right? So I will now go on to and let us, like we did yesterday, right? I would like to request people that in case you have questions, please do not hesitate to ask me those questions. You please stop me while I'm this thing. Okay. So now what happens is, when we are actually looking at objects, right? I'm now going to talk about photometry and the BANZAI pipeline, which is used in the LCO, right? We know what the LCO is, 26 telescopes, 7 different locations. Now, what is photometry? Okay, let's talk about photometry. So photometry is obviously, photo is light and meter is measure. So you're basically measuring the light or the flux from a source of light. Okay. Now, so when the light is measured through a telescope, either you use a photometer, this is what was used earlier, and now what is more used is what is called a CCD, right? A CCD is a digital camera, and it's basically okay. I have not put an image over here, but basically a CCD. It's like an array of buckets. Okay, think on XY you have buckets, and in each bucket you are filling photons. Okay, now so these different photons fall on the buckets, which is a grid. Okay, of pixels, which is a picture element, is a pixel. Okay, now it basically works on the simple principle called photoelectric effect, and that is basically that if you have light falling on a metal, for example, you'll have electrons being emitted from that metal, and that is what basically creates a current, right? And that current is what you are going to measure. So you have, just think of a digital image like a grid. Okay, it's an XY grid of counts. Okay, so at different points, at each point, at each bucket, it basically measures the amount of counts, or the intensity of the light which has fallen on it, right? So with that you can actually measure the brightness, because you actually have the counts. Okay, now how do we actually measure the luminosity or brightness of a star? Okay, so this is in basic physics courses you will do it, Stephen Boltzmann's law, where the luminosity of an object is basically proportional to T power 4. Okay, that means the temperature power 4. If your temperature doubles, the luminosity of an object goes 16 times, right? Which is something we can feel now in summer. When the temperature rises, by every degree it rises, the heat increases as a factor of to the power of 4, right? So you actually, like I'm saying, you double the temperature, your luminosity becomes 16 times, because it is to the power of 4. It also depends upon the surface area of your source, right? So typically, if we are talking about a star which has a radius of r, so therefore your surface area is 4 pi r squared. If you're assuming a circular star, then 4 pi r squared is the is the surface area, and sigma is Stephen Boltzmann constant, and T is the temperature of the star. So the hotter the star, the brighter it will be, right? Now what applies is called the inverse square law. That means as you move away from a source of light, the luminosity will decrease as square of the distance, because it is basically this area, right? It is basically this area which is there at different distances. So as you're going, as your distance increases, this thing actually goes as the square. So rather it goes as 1 by square, right? 1 by square. Inverse square law is it's a law which is very commonly applicable in many phenomena in physics, which includes Coulomb's law, gravitational law. It also applies for luminosity. We can talk about that at some other stage. Okay. Now in astronomy, we basically have a unit of measuring brightness, which is called the magnitude. Okay. So we measure the flux of the source, and based on the flux of the source, we actually measure what is called the magnitude. Now, this is a picture of Hipparchus. He actually looked at stars. This is obviously, this is pre-telescope times. And therefore, when he looked at stars, the brightest stars, he called them 1. These were like order 1 stars. Then the first magnitude stars. The second magnitude stars were the less important ones, and the third and the fourth and the fifth and the sixth. So in those good old times, the brightest stars they could manage to see were what are the sixth magnitude stars, which we obviously do not manage to see in today's times. But they did that in this thing. And therefore, the two factors which actually define the magnitude of a star is number one, the distance of the star, and number two, obviously, the intrinsic brightness of the star, right? However bright the star is. These are the two important factors which define the magnitude of a star. So you have magnitude 1, 2, 3, 4, 5. And what Hipparchus measured is that if you have a magnitude difference of 5, it is equivalent to a star being 100 times brighter. Okay, so 100 times brighter. So if you actually put it 100 to the power of 1.5, you will get 2.519, right? So that is the factor by which the brightness of stars varies. So 2.51 to the power of 5 will give you 100, right? So if you have a magnitude difference of 5, you will get a difference of 100 in brightness. Now, so we have this simple formula, 100 power 15 is this. And based on that, we define this as the magnitude scale, right? So these are the magnitude scales. So like I said, 5 magnitudes difference is a 100 factor in brightness. And you can actually put this in the form of a formula where I can take a ratio. If I have 2 stars, I'll put a ratio. I can take it one by the other, and I can actually put it and define the brightness, right? The other important factor we said about the star is its distance, right? Now, the distance to the star is something very critical because, obviously, again, as your distance increases, the star becomes fainter. But how do we measure the distances to stars? The easiest way in which our brains work, for example, if you look at this image over here, you see both these people looking at these two peaks and try to estimate the height of this tree. A very simple way is if you can measure this angle and you can measure this angle, you'll get this angle. Half of this angle is nothing but the parallax angle, right? So you can see over here, it is the parallax angle. That means you measure the angle subtended by this object from two different positions, right? Now, the easiest way for us to do it, which we regularly, on a regular basis, we do it, is with both our eyes, right? So the baseline is the distance between both our eyes. And then we actually look at an object and we estimate the distance. So you notice that if you close one eye and you try to estimate distance to something, you try to touch your finger, it'll be difficult for you to do it because you do not have both the eyes. But if you have both the eyes, you can actually use that to get an angle and get the distance, which is the parallax angle. So once you know the parallax angle, you can find the distance. For stars, the simplest way is, obviously the baseline of our eyes is too small because stars are very far away. So what we instead do is we make the baseline the Earth's orbit, right? So we know that the Earth is going around the sun. Supposing it's here in Jan, it will be here in July. So I look at a star in Jan and I find out the angle. Then after 6 months, I look over here and I find the angle over here. Half this angle is what I call the parallax angle. If this, I call it 1 unit, this is called 1 astronomical unit, which is 150 million kilometers, then you can actually get your distance to be 1 upon the parallax angle, right? So if the parallax angle is in arc seconds, you define the distance in a new unit in astronomy, which is called a parsec. So a parsec is the distance at which you will subtend a parallax angle of 1 arc second. Okay. So that's the parallax angle. So you can actually define the parallax angle. If I have a star, I check the angles it subtends at different points of times and I get the distance. Now, when we look at objects, we measure their brightness, right? And what we have to do is, because we had that, you saw that power which we do, we basically find out the flux and we convert it to what is called a magnitude scale. In principle, the magnitude scale is a log scale, right? Because we have our 5, the factor 5 coming in, and therefore it's 2.5 times log of whatever is the brightness, right? That will give you the magnitude scale. And we have what is called the apparent magnitude. That is the brightness of an object when we see it from the place we are observing it, okay? And you can actually use that to find the apparent magnitude, right? I just noticed that there are some, Priya, is there something on chat? Are there questions? Okay, okay. I can see that there are some questions. I will answer those questions.
Ma'am, you can continue. We can take because there are few questions, so we can take.
Okay. And maybe you can share that YouTube link. Like I mentioned yesterday, is we are already live streaming on YouTube. We need to mute someone. So we are already live streaming on YouTube. Okay. So since we are already live streaming on YouTube, it's already there, right? And if you have the link which has come to you in your email, you'll actually find it. There are no pressing questions, no? I will
No.
just, somebody is muted, or what is the thing? Let me stop this. Okay. Okay. So the the apparent magnitude scale is the magnitude which it appears to us, the apparent magnitude. And based on that, the sun is super bright, and therefore the sun has an apparent magnitude of minus 26. So the magnitude scale is a reverse scale. In the sense, the lesser your number, the brighter you are, right? Because you remember when we started it with Hipparchus also, magnitude 1 star is a very bright star, and magnitude 6 star is a star which is 100 times fainter than that, right? So the way it was set up, this has actually just happened historically, that the way the magnitude scale was set up, the lesser your magnitude, the brighter the star is, right? So in that way, we have this apparent magnitude scale. You can see that the sun is minus 26, the full moon is minus 13, Venus is minus 4, Polaris is this, right? This is also telling you the capacity of telescopes, how faint that they observe. So a 1 meter telescope typically can see up to, we with our eyes, we can see up to 6th magnitude. That's the naked eye limit. A 1 meter telescope will give you 20th magnitude. The Keck telescope will give you about 30 magnitudes. It depends upon the sites. So how we put up our magnitude scales is basically by putting a 2.5 times log of the ratio of two stars. Now, this is the apparent magnitude scale, but since we want to compare stars, like I said, the same star is going to look fainter if it is further away from me, and therefore we convert it to what is called an absolute magnitude scale. Now, an absolute magnitude scale is the brightness of a star if it was at a distance of 10 parsecs. Okay, so this has been just picked up because it's like, for example, I have many different sources of light. I don't know which one is more brighter, so I get all of them to the same distance and I compare their brightness, right? So that's exactly what the 10 parsecs mean. You get all the stars to the same distance and check out the difference in their brightness. So the 10 parsecs is that. We get them all to this. So therefore the formula which you can see is this, very easy formula to remember. If apparent magnitude is small m and absolute magnitude is capital M, then small n minus capital M is equal to minus 5 plus 5 log d. So if your d is equal to 10, this will become 1, this will become plus 5 minus 5. That means m will be equal to m. So the absolute magnitude is the magnitude of a star when it's at a distance of 10 parsecs. So with that you can get this thing. If the apparent magnitude appears to be lesser than the absolute magnitude, then the star is at a distance less than 10 parsecs. If the apparent magnitude appears larger, that means it is fainter than the absolute magnitude, then it's at a distance larger than 10 parsecs. This is important because we need it later on for our work. Now earlier what happened is photometers. Photometers, that means you have light falling on from a photocell. It falls on this thing, you measure it with a galvanometer, and with that you measure the brightness. So old telescopes had these photometers with which they can be this thing. But even now in many universities, for smaller telescopes, often people use photometers because they are easier to construct. You can actually construct a photometer quite easily. One can actually do a workshop on constructing photometers, which you can connect onto your telescope, and with that you can actually measure the brightness. So that's what it basically does. So what we basically do in photometry is that you basically want to measure the amount of photons coming from a star. So obviously first thing is you center the image. It has to be centered at the star. And the other very important thing is the estimation of the background level, right? How much is the brightness in the background? And then you measure the flux in the object of interest. So the object flux is obviously going to be total counts minus the sky counts, because in the total counts is already sitting the sky counts, right? Sky counts are sitting in that. Therefore, I need to subtract the two. And therefore, for that reason, estimation of the background or the sky level is very, very important so that you can get the right brightness. So we are not going to do this today. We don't have time to do this, but this is a software called the APT tool. You can download it. It's a free software. It's available on the internet. It's called the APT tool. And with that, you can actually see how to measure magnitude. Typically, what you're doing is that it's like you make a hole. You make a hole around the object. Okay. So this is done so that I can collect the total flux of the light coming from the object. Okay. So I make this white circle, which is collecting the flux coming from the object. Now I also want to estimate the background well, because the background is sitting in the object also, the brightness which is coming from the object. With this I also have the background. How do I find the background? I basically make an annulus. I make an inner annulus and an outer annulus, and I measure the light in this annular region. Okay, and that will give me the value of the sky brightness. And then object is obviously object minus the sky, the background annulus. And this was very nicely done with the APT tool. So you can actually make growth curves. We won't go into these details, but what is the size of this white circle, right? Which we had, the white circle in which you were letting in the flux of the source. You will see that if I increase this aperture radius, if I keep it small, then initially I'll have lesser flux coming in because I don't have all the flux from my source. At some point it will peak, and then if I continue increasing the size of this white circle, right, then it is outside the source. So obviously then the flux will fall. So what you're seeing in the growth curve is, if my flux is small, if my circle is small, it's getting only partial flux. Then there'll be a size at which it is optimum. And then if I further increase that size, again the flux will fall. And this is called the growth curve. This is used to determine what should be the aperture at which I should collect the light from the source. Okay. So that is what is this. We also do a thing in measuring photometry, which is called two-dimensional profile fitting. If this is the brightness from the source, which you see in this hump, we actually fit this curve to a function. We may fit it to a Gaussian function, for example, or maybe a Lorentzian, or we fit it to what is called the point spread function. The point spread function is the spread you get from a point source of light, right? And you use that to basically get the brightness coming from this. And with that, you can measure the flux which is coming within this thing. So there is a software called Fort. We'll do this on another day. We can't do this today. But Fort is basically a profile fitting. This is called profile fitting software. So the first one which we did, aperture APT tool is an aperture photometry. In aperture photometry, you're just making an aperture for which you can measure the brightness from the source, and then the outer part with which you're getting the sky. But the other kind which we spoke about is what we call profile fitting, because this depends upon the kind of profile you're getting from a point source. And then you fit it and you collect all the light within that thing, which is down doing a software called Fort. This is also available on Python, and you can actually use this to measure the brightness of a source. Now with that, you can actually measure the brightness, and these are the two techniques of doing photometry. Either you do aperture photometry, but the more accurate version instead is the profile fitting, right? Because the aperture thing, it's assuming a spherical symmetrical profile, but in profile fitting, it will fit it to whatever kind of a profile it actually gives you, right? So you accordingly take whatever that profile is. Typically, if you're looking for a variable star, easiest way is you take an image. You can do this with the LCO also. You take an image. This is exactly what was being done with Astrometrica also yesterday. You take an image 1 and you take an image 2 of the same part of the sky. And then what you do is you subtract one from the other, right? If all these sources have the same brightness, then when you subtract that, they all cancel out each other, right? But the one source which has changed in brightness, in this case it is this source, you can see it pops up, right? While all these other sources which had similar brightness in both the frames, they do not show up, right? The similar thing can be even done like with what we did yesterday, Astrometrica. That means you have the background stars. If they all sit together one on each other and the asteroid is moving, then that will show up in the difference. So this is called difference image photometry, where you actually take the image of a region, you take it again, subtract it, and all the things which will pop up will be the variable stars. All the other sources will be cut off, right? Because we assume their brightness is approximately the same. So you can see this is the difference image, right? Where you can see all these other objects have been cut off because their brightness is about the same. Only this one thing pops up, which is the bright thing. So this is another method in photometry, which is called the difference image photometry, where you take differences of images. Okay, this is also a standard technique which is used for photometry. Another very important thing when we do photometry is we use filters. What are filters? Filters are basically, they permit light of a certain wavelength, right? So for example, if you're looking at this one, this is an ultraviolet filter. So this one, it centers somewhere around 3500 and it has a width. The width you can see is about 500, not even 500, maybe 300 angstroms. So the center is 3000. This is in nanometers, okay? That's why I'm saying 3500, but this is 350 nanometers, right? So 1 angstrom is 10 power minus 10 meters. So this is actually 350 nanometers is the central point for the ultraviolet filter. And maybe you have a width, if you take the full width at half maxima, somewhere over here, maybe it has a width of, I don't know, 150, 200. This will be, if this is this and you say this is maybe 250 or something like that. Totally 250, so 125, something like that. So this is the U band filter. There's a broader filter called the B band filter, which centers somewhere around 450 nanometers. This is the V band filter, close to 5500. The red filter is a wider one, which has a longer this thing. And you have these different filters. The basic thing about filters is it basically permits light only of a certain wavelength with a certain width, right? That's what a filter does. So when you measure the photometry or the brightness of a star, you measure its number one, its magnitude, and you measure that magnitude in a particular filter, whatever the filter is. Okay, so that would be the filters. Now in LCO, what it does is when we give the request to observe, we will give that now. You'll see that um, it basically runs a certain pipeline which is called BANZAI. BANZAI stands for Beautiful Algorithms to Normalize Zillions of Astronomical Images. Okay, and basically that is what gives you processed data. So that is what is called the BANZAI pipeline. So I'm going to now exit and I will come back inside. So I will first exit and I will now share. Are there any questions? Right. I hope you can see my what do you say? Can you see my browser?
Yes, ma'am, we can see that.
Oh,
The
great.
submitted observation request, the page.
Yeah, so this is the LCO observation portal. Okay, I have logged in as Priya Hasan. That's why I can observe. If you log in, you go onto this website, you will not be able to submit an observation request because you do not have time on it. Okay, but I will tell you what you can still do some things. And if you still want to observe, you tell me and you get this thing. So let us first submit an observation. We want to observe. We understood what are magnitude scales. You understood what are these things. Let us say we want to. So let me this thing. Let me call it, for example, workshop. Okay. So we are calling this workshop. Proposal. My proposal is under Shrishti Astronomy. That's where we actually get our observations, right? So, if you remember when I told you, LCO basically runs with a scheduler, right? A scheduler basically, you are not sitting on the telescope, right? So you give a request. You say that you want to observe something, right? Some object, we are going to say that. And when you want to observe that object, you are actually going to, you submit your request. This is your submission of the request, okay, to get observations. Now, there are different acceptability thresholds. You may check what a quality of data you want. If you just leave it to the default values, certain things there's no need to change it. So we can leave it as it is. Okay. Now, I said that for the 40 centimeter, when we are using it, we are basically using this instrument and you can only do imaging. You can't do spectroscopy. If you had access to the 2 meter and the 1 meter telescopes, then here the observation type, you would have had a drop down for spectrum, right? But since we are using this thing, we do not have access to the spectroscopy, right? So we say we are taking an image and we are looking at this. If you want sub exposures, we don't need that. So we'll go in for exposure time. Okay. Now you can see how many exposures you want. Say you want 1 exposure or you want 5 exposures. Just to be easier, I will take it only 1 exposure. And I will say, let's say in seconds, let me say it's 300 seconds. Okay. This is the readout mode. We won't disturb this. Now remember, I have already explained to you what are filters. Filters are, objects which will only permit light of certain wavelengths to pass through the telescope. So there are many filters which are available. These are the Bessel. These are very common ones which are called the Bessel BV filters. H alpha filter is a certain filter. Now filters, like I said, basically they are different wavelengths, right? So for example, the H alpha filter, it is centered around the H alpha hydrogen line, right? Now, therefore, in this case, what if you put a H alpha filter, it will basically show you H alpha emitters. That means which of the stars that you are observing are actually emitting in H alpha, right? So that similarly, this will be O3. So for example, you will actually see what is the O3. I hope you know what does O3 mean. This is triply ionized oxygen. Okay, in In astronomy, when we write H1, H1 means neutral hydrogen, right? H2 means singly ionized. So this is doubly ionized. So O1 will be normal oxygen. And if I doubly ionize it, that means I remove 2 electrons out of it, it will become O3. So if I want to see the oxygen line, I may put that filter. Similarly, there are other missions which are going on, other telescopes. There is the PAN stars, and they have these two filters called the Z and the W filter. There's the SDSS, which has the GIRU. These are the SDSS filters. So you can take whichever filter you want, right? Let us say, for example, you take the Bessel filter, okay? And if there is an offset in this thing, whatever. We can leave this as it is. Don't worry about it. Now over here, I can put a certain, we are looking at star clusters, or I won't put 2682. Let me put my favorite. I always put NGC 1960. So this is a certain star clusters. If you want to see the star cluster, I'll show it over here. This is a cluster which I studied way back in my PhD days, and that's how somehow it's my favorite cluster. It is called Messier 36. This is the cluster, which is over here, and it's a cluster of stars, okay? Nothing special about it. Just like I said, it is one of the clusters I worked in for my PhD work, so I like to always look at this cluster. Okay, so this is NGC 1960. Now what it has done, it has actually used it to find out its RA and DEC, okay? RA DEC is the coordinates of this, and it's already telling me that there are 499 existing frames in the archive of this object. So it already has so much of data already of its object. So it's trying to warn me that if you, you needn't observe this object because already we have so many observations of this object. If I want to listen, I can listen. If I don't want to, I needn't listen. Okay. So now when you're tracking an object, if you're tracking stars, stars basically get tracked with the rotation of the Earth. So that is what we call sidereal tracking. If, for example, you are looking at a comet, for example, then in that case, those are not considered sidereal tracking. Then it is what is called non-sidereal, right? So for example, if I was looking at, stars basically get tracked. Sorry, if I was looking at for a comet, for example, I may choose a non-sidereal tracking, right? So I may look at different kinds of trackings, which could be useful for me, right? So since we are looking at a star cluster, we are going to do sidereal tracking. But if you are, for example, studying a comet or something like that, which is non-sidereal, then you may actually go on for non-sidereal tracking. Now this is the epochs. These are the RMA DEC. Now the maximum air mass. I didn't get a chance to explain to you air mass. You know that when you're looking at zenith, an object in zenith, you go through minimum atmosphere. But when you're looking at an object, supposing here, you are going through more atmosphere, right? So air mass 1 is if you're looking at an object at zenith. As you come down, obviously the thickness of the atmosphere increases. And obviously the amount of air or extinction or loss of light because of the atmosphere increases. Now, obviously, the larger ideally you would like this object to be at zenith, at 1. But probably it's not at zenith. So therefore we say, okay, we'll allow a flexibility up to 1.6, but we may not take more this thing. Similarly, we also define that, see, it's going to basically check up for all our 26 telescopes, right? You want to say if the moon is also out, right? How far should the moon be from my object, right? So I can give my minimum moon separation. I can say at least it should be 30 degrees away from the moon, right? And the maximum lunar phase, which I will allow it. Otherwise, what will happen if it is too close to the moon, right? Then all the moonlight will come and contaminate my image. So all the brightness I get will all be wrong because it is basically it's basically collecting moonlight, right? So I can add this thing. Obviously, if I were to take maximum air mass, say 1.2 or 1.4, then I would get more accurate readings, right? But only problem would be is that then the scheduler has to wait for a point in time where it can observe this object with the given air mass restriction which you are asking it to do, right? Similarly, even about the lunar separation, 30 is what is advised by LCO, but if you give it, say, 90 degrees, right? then maybe it may just take longer to find a point in time when it can observe it with 90 degrees. So there's nothing to lose in that, there's no problem. It's just that it depends on what restrictions you put. Okay. Now comes the interesting part. Look at this. This one is basically showing me the visibility. Okay. That means, see, these are different telescopes. One is the McDonald telescope. This one is in Hawaii. This one is, I think, the Chile one. So you can see all these three telescopes. And for these, it's basically showing me what's the different air mass which it's going to get for these, right? Today, this is basically on Sunday, 20th April, right? What is the different air masses which it's going to be getting for this object, right? So this is basically how do you know which object can you observe in the sky on a given day, right? Now, I will just briefly describe that to you, that you know that objects in the sky are given in coordinates RA and DEC, right? Those are the coordinates for objects in the sky. Yeah, okay. Fine, some people on Topcat. Okay. So the thing is that what happens is on 21st, you have to basically remember it like this. On 21st September at midnight, right, you will have an RA0 object right overhead, RA0 object. Now the RA changes by 24 hours and 12 months, right? So every month it changes by 2 hours, right? So for example, if I were to check it on, so if for example on 21st September you have RA0, right? And then let us say that what is your observation time? It is minus 6 hours before 6 o'clock in the evening to 6 o'clock in the morning, let's say. So that means if you are observing in September, you can observe objects which have an RA ranging from minus 6. Minus 6 is what? 24 minus 6. That means 18 to 24 plus 6, rather 0 plus 6, which is 6 hours. So 18 hours to 6 hours objects you can observe in the night. But obviously 18 hours will be very low on the horizon. 6 hours will also be low on the horizon. So accordingly, you may choose which are the objects you observe at that time of the year, for example, right? So you have to basically check what is the RA of your object and what is your time of observation, right? That will define the RA of the object which you can observe for that time of the year, right? The other important thing is your latitude of your observations, right? For example, if you're in the southern hemisphere, you won't be able to see many northern hemisphere objects and vice versa. So depending upon you basically have to take it as 90 minus 5. Whatever is your latitude, you will see the 90 minus 5 objects will be observable. Other ones you will not be able to see it, right? So ideally speaking, this is an interesting plot which you see over here, which is the target visibility calendar. That means it's telling you these objects are visible like this over here, right? If you want to do it for another object, I may take it for another object. I may say 2384. This is another object, right? 2384. You can see it's revised it, given me my right ascension and declinations, given me this, and now it's actually plotting my visibility. Now you see this one has slightly better visibility. Like I told you, one is the best, one is zenith. But you see these guys, you can have closer to one with this and this, right? And this is with the Siding Spring Observatory. This is in Australia. Sutherland is in South Africa. And therefore you can accordingly choose. So supposing if let us say we chose this object. So you can see it's nicely observable from all these different observatories, right? So therefore I can say okay, I can observe this object from different observatories. So now we come to the first advantage of having used a robotic telescope. Number one, you understood how you're getting the object. You are actually defining how much to keep your exposure time. We've just taken 300 seconds, but you can take whatever you want. This is the filter in which you are observing it, right? So you have a choice of filters, whichever filter you want. And you can actually, so you can see this one, 374 frames are there of this, and you have this. And I can now, what I can do is, since I've seen all this, I can actually submit my observations. So I can say submit request here. And it will say it will take approximately 6 minutes, 42 seconds of telescope time. because I told you I have 100 hours of time, so it's awarding me. I can say okay, right? So I can say I'm willing to give that time. So now what it is telling me, my request has been submitted. So my target is, this is another star cluster. I can show it to you what it looks like. This is NGC 2384, also one of my PhD clusters. This is the cluster, and you can see this is the cluster. And what it's basically doing is it's observing this one. So it's saying this is the target, this is the RA deck, this is the guiding, this is the stuff, and now the request has gone, right? So now I am going to very soon get later on email as which will tell me when these observations are done. To plot an HR diagram, I need it in one more filter. So I'm going to plot it again, and I'm going to do again NGC 2384. Okay, I'm going to again do 300-second exposure, right? So I'm going to, hopefully we'll plot an HR diagram, and therefore here I'm putting for 300 seconds, I'm putting this, and I'm going to put another filter. So where is the filter? The filter is, where is it? Exposure time. Yeah, here's my filter. So I'll put the filter as Bessel V. Okay. So I've put a 300-second exposure for the same object with Bessel filter V, and my parameters are here. You can see the visibility is the same object, therefore the same visibility data, and I can submit my request. Everything is there? No. It wants me to give some more data. 1 minute. It is all here. Okay. It wants this stuff. So I'll say workshop, and I'll say my proposal is Shrishti. Okay. Now hopefully I can submit my request. So now I've submitted my request for V-band data. I had submitted my request for B-band data. Now I'm getting for V-band data, and I've submitted all this, right? So what I'm actually going to get is in my email, I will actually receive an email when the observations are done, right? So we will leave this as it is, and we will continue with our talk of what we were doing. So I am going to, I'll go back. Are you seeing my PPT, or are you seeing the Chrome? Maybe I can stop share, and I will share again and get back to my PPT. I hope you can see my PPT now. Can you see my PPT?
Yes, ma'am, we can see.
Perfect. So to save time, because like I said, we've got to give the request, and after that the data will come, right? And that's why now I've already placed our request, and let's hope that the data comes before we get over, right? It often comes fast enough. Let us see. So what LCO does is, it, like I said, you saw the process of actually giving a request. We actually gave a request for data. What are we doing? We are trying to observe a star cluster NGC 2384 in 2 filters, and we've given a 300-second exposure request, and it's gone. Okay. Now the scheduler is going to basically check all the telescopes. You saw the visibility data which was there for different telescopes, and each of them there'll be other requests also for the telescopes and objects. So based on that, the scheduler will decide as to which telescope should observe our source, right? The scheduler does it on its own. You do not have, we don't play a role in actually, what do you say, guiding the scheduler. The scheduler decides on its own. We do not have control over that. It just does its business. Okay, so once we give that thing, the process data. So here is the thing. We actually on site, we observe the thing. Now what happens is the data which comes in, it goes into the LGOGT headquarters. Okay, so they actually receive the data which comes. Okay, and then they actually have a pipeline called the BANZAI pipeline, which we just spoke about. And the BANZAI pipeline actually gives an output which users can use. But since there could be users who want to work with raw data, that means the original data, and then they want to do things with that data. If that's the case, then it also gives you access to the raw data. So you can actually have a look at the raw data or the processed data, depending upon whatever you like to do. So there are papers. I have not. Yeah, I have not. There are papers which actually describe the BANZAI pipeline, right? And you can actually have a look at that, see whether you are convinced about the pipeline. If you are not convinced about the working of the pipeline, which can be a possible case, because when these things are in an automated mode, right? In an automated mode, if you have a pipeline, then sometimes it can happen that human intervention can give you a better result than the result you get from the pipeline, right? So what LCO gives you, it gives you the freedom. You have both available to you, and you can actually choose which one you would like to, which one would you like to use, the raw data or the this thing. I have different workshops where we actually showed people use of the raw data as well as use of the processed data. Today we'll only work with the processed data because we do not have time for the raw data. Okay, so what does the BANZAI pipeline do? Now, when you take a CCD image, right? When you take a CCD image, there are various things you do. First of all, is that you could have bad pixel masking. You could have certain pixels, picture elements, which have got spoiled. See, this is basically a piece of electronics, right? So it can happen that a certain pixel has actually got spoiled. It could be what we call hot, that means it gives you a higher reading. It could be cold, it gives you colder reading, or it doesn't give you any reading, right? It could be just black or white, right? So what happens is that you have to mask the bad pixels, because they are the ones where the data which you're getting from them is not important. You want to ignore that data. So then you do what is called bad pixel masking. Okay. Now, because this is a piece of electronics, and remember I told you about the photoelectric effect, which actually causes the current in each of these things, you want the current to move. And for the current to move, we basically add a bias voltage. We add a voltage to the system so that the flow of current takes place. Okay. So this is what is called the bias, right? And therefore, when we get our reading, we subtract the bias from it. You can actually see the bias. In a CCD, we also have a dark subtraction. That means if you don't expose the CCD to any light, right? Don't expose it to any light, you will still get some brightness, okay? And that brightness is what is called the dark reading, or it is the dark subtraction. So the dark is obviously sitting in all your data, right? Because that is the reading which the CCD is giving without any data. That's the dark reading. So you may actually want to subtract that from your main object reading. The other thing you have is what is called the flat field subcorrection, right? So basically what happens is when you have a CCD, for example, this is a 2K CCD, 2048 by 2048, right? So electronically, when such a thing is produced, what happens is that you will, there could be a chance of, rather it is a chance that each pixel behaves slightly differently, right? Each pixel behaves slightly differently. And therefore what we do is we also, these are all called calibration frames, the dark frame, the flat field. We actually expose the CCD to uniform brightness, okay? Some brightness which is uniform, okay? And then we note what is the reading on every pixel. Ideally speaking, each pixel should have the same reading because they're getting the same brightness, right? But in reality, they do not give the same value, okay? And therefore, that actually gives us an estimation of the behavior of each pixel, right? So that means you know how does a pixel react. So supposing if you have a certain reading, you will actually know whether this pixel has overestimated it or underestimated it, because you already have a flat field image which has kind of calibrated to check what is the value of the reading in different things, right? So you can use that. And so BANZAI does that. These are called calibration frames, which is done to correct the CCD image. So from all images, you subtract the dark, you subtract the bias, and you divide by the flat, okay? And with that, you can actually get a cleaned image, okay? Another thing which BANZAI does is it actually extracts sources using something called a source extraction software. It's called the source extractor, and it actually extracts all the sources, right? So that is, and it also does astrometric calibration, gives you the RAs index for the sources. So the final data which we get is made up of what is called a FITS file, And the FITS file actually has 4 extensions. So we'll actually see it. One is what is called the science data, SCI. One is the bad pixel mask. One is the error file, which is giving you pixel uncertainties. And one is the catalog file. So the catalog file lists the pixel positions and the fluxes. We'll actually see that, okay? And basically does that for us. So this is an example of reduced frame for the BANZAI pipeline, and it actually gives us. So you can actually, we'll actually see this and work with this. So this one, I'll exit this thing, LCO Photometry 2. I will open LCO Photometry 3. Okay. Now another thing which we need to take note of, I hope you can see my thing, right? Okay. Is that we have to also standardize our magnitudes, okay? Because the brightness which you may get from the, with the reading which you get is in the scale of the instrument. So if we want to standardize brightness, right? So first of all, what we need to do is, like I told you, you have your filters, you have these filters. You will measure the flux, we'll measure the flux coming from every source. Then we can convert that to magnitude scale. We'll do 2.5 times log of whatever that is. Then if you know the distance to the source, you can actually find the distance modulus, okay? Now, today we are not going to use Gaia data, but if you were to match your stars with Gaia data, which is something you can do in the future, you can actually find the distance to individual stars. So once you find out the distance to individual stars using Gaia data, you can actually calculate the absolute magnitude from the apparent magnitude, right? So that is something which we've done, but today we are not going to do it. We just work with apparent magnitudes. Maybe we won't have the time to work with absolute magnitudes. So here are our things. We can find out the color index, which is difference in two filters. And we do these things. We don't worry too much about these. You can also, what is done in astronomy very often is the observation of standard stars. Okay, so we do not know how to scale the brightness of our stars. So what we do is that there are certain stars which are called standard stars, right? Which are there in certain catalogs where we say that the brightness of a certain star is something, right? Using that catalog. So what we do is, while we are doing observations, we observe the standard stars, right? So supposing if when we are observing it, our star appears to be, for example, 12th magnitude, right? But for example, when we compare it to the standard star catalog, we discover that this star actually has a magnitude of, say, 9th magnitude, right? So then I shift my standard stars by that required amount, and I accordingly shift all my stars by that required amount, which I measured using the standard stars. Obviously, the more standard stars I do that with, the more accurate will be my measurement of this flux, so that when I'm converting it to absolute magnitudes, I can convert it correctly, right? So these are my photometric standard stars. I may also do an air mass correction. That means I have the air mass measurement. When you get your data, it tells you what is the measurement of the air mass, and we can actually do it to convert it to the brightness if air mass is equal to 1. Okay, this is the way you convert it. So you convert it, your B band magnitude, you could add a 0 point. You could also have a standardization factor which depends on color, as well as a factor which depends upon air mass. Okay, so this is a little difficult procedure. We will not have too much of time to do that today, but I'm just telling you so that this keeps you informed that this is the way we actually do it. And hence we get our magnitudes and we get our magnitude scales. So for each of the instruments which we have, for each of the filters, there are different 0 points which are provided to us, which we can actually use for the data analysis, right? We won't go into too much of detail of that today because we don't have the time for that, right? Now the next thing which I want to rush through, is I'll talk a little bit about this, is CCDs, right? Like I told you, these are what we call charge coupled devices. So earlier when photographs didn't exist, people actually do drawings. They actually drew what they saw. So even Galileo, we have actually drawings of Galileo when he observed things with his telescope. He actually drew it, right? Later on, we had photographic plates where people actually could get it on. So these are drawings, these are Galileo's pictures also. Then you had photographic images where you put a photographic plate. Okay. Photographic plates basically depend on, you basically have this silver halide salt which is kept. And when that gets exposed, it actually darkens. And that's how you get your negative. From the negative, you produce the positive, right? That is photographic imaging. Now, photography is very, we won't go into these things because I'm going to run through it. But later on in development in astronomy, when the space telescope, Hubble Space Telescope was being launched, that's when they discovered what are called the CCDs, the charge coupled devices, which I spoke to you about. It's basically a grid, right? And you have this date, it's like a grid, XY grid. This is a picture element. And when you expose this to light, each point will get a different amount of electrons. You measure the current in each of them, and using that, you can get counts, right? Now, if you put a filter on it, you will get different counts based on the filter you use. So I told you this is based on photoelectric effect, and basically it means that you have buckets. You collect the photons in every bucket, and therefore you measure the amount of current coming in each bucket, right? I'm sorry, I'm kind of rushing through this basically because we do not have too much of time. So in that way, you actually read it and you check the data you're getting in every bucket. I also told you about what I spoke about just a minute ago. I'll just show that to you just to make it clear. Just a minute. Is the calibration frames. I was talking to you about calibration frames. And here you can see. Yeah. So you can see that you could even have in CCDs, you could have lots of problems. You could have a charge filter from one to another. And so, like I told you, what was I was expecting is the data has already been emailed to me. So we are going to get the data. I hope I can share it with everybody over Zoom. I'll just try to do that. So you could have blooming in a CCD, you could have image defects in CCDs. All these things have to be corrected. Like I told you, you have bias frames, you have dark frames. This is the frame without any exposure. This is with uniform exposure, which is called a flat field. And we can use this if you have a science image, you subtract the dark. From the flat also, you subtract the bias. You do science minus dark, divide by flat minus bias, and you get your output image. And this is what is called a cleaned image. And this is, you can use this book, a very good book, which actually describes CCD astronomy, right? So have a look at this book and you can see that. Okay. Now, let us, I just now got a message which basically told me that the data that we asked for, I will say stop share and I will say share. Actually, I should just be sharing my whole screen, maybe. Okay. So here you can see request workshop has been completed. So here you can see data may be downloaded over here. You see how fast the data comes. So here is my data. You can see here is the thing. It says it's finished this thing. It's finished the target of this one. And this is the V-band data. Okay. This is not the B-band, but this is the V-band data. So I can say I will download it here. Okay. This is my download data. And I can say this is this LCO data one. Okay. So you can see that the way the file has been this thing. I am going to actually share this, I think in the chat. I'll just check it in the chat. I think you can add a file. Yeah, here, this is a file. No, this is this. No, I can on my computer. Okay. So I'm sharing this file. I hope all of you can access it. Prerna, if just see if they can't access it, you can email to it. It's only a 5.48 MB file.
Sure, ma'am. I'll do that.
It's there on this chat now, right?
Okay.
If I hope everybody can download it, or you can just email it to everybody because if there are people on YouTube, then they will get that, right? So this is just the, you can see this is the date 2025. Today is the month 4, April, and this is the date 19th. So the name of the file is by the date. Okay. So this is basically the B band data which we have. Okay. Now I already saw that there were, you are seeing my browser or what are you saying?
we are watching the screen. I think you have shared through the entire your
Yeah, so you
system.
can see my browser,
So
right?
we can see the browser now. The Google
Yeah.
page.
So I had requested ma'am to tell you all to download Topcat, right? So there is Topcat. Did you all Topcat astronomy? This is at the University of Bristol. I hope all of you all can see this. Go on to this Topcat page and I requested you all to download it. Topcat is a Java-based software, so it will work on any operating system, whether you have Windows, Linux, Mac, whatever. It will work on anything. Okay. This is a part of what is called the virtual observatory, which is a this thing in astronomy where it's basically trying to help people access data of different kinds, right? So therefore, please have a look at this and look at this and this is the person who actually did it. He's called Mark Taylor and he actually did stuff for us in Shishti astronomy. You can see the link to the videos and all are also there. You can actually use this page to see some of the tutorials. You can see there are tutorials over here and there is also stuff which he did with us and other YouTube videos, very nice ones, which are available on this. Okay. Now, what you need to basically go down is go to downloads and download this Topcat full.jar, right? Download this. What you need on your system is you need to have Java also, right? So you need to have Java running on your system and you need to download this file. I had requested you all to do it. So if you're using a Linux system, you will have to give the command, you'll have to say java minus jar topcat.jar. If you're using a Windows system, you just double click it and it will open, right? If you have a Mac, you'll have to say brio install cask topcat, no quarantine. And for a Mac, if you have, you'll have to download the DMG file, right? So for Windows and Linux, you'll use topcat full.jar. And if you are using what do you say, a Mac, you'll have to download the DMG file, right? So please download this and this thing it. And here, this is, you'll get an icon which looks like Topcat, which is from cartoons. And if you click it, this is what Topcat looks like. I'll just remove what I had sitting on this. I don't want to look at this. Okay. Okay. So I hope everybody is has actually got Topcat running. If you don't have it running, don't worry. Listen carefully to what I'm telling you, and then later on you can actually use it to download it. I think I got another mail from LCO, which may be the B band data. I will look at this, and no, it is not there. It's just only one data set. Okay, so the other data set still has to come. Okay, so now the file which you'll actually see, right? This is the file which you've got from, yeah, this file, like I told you, LCO data 2025 419. This is April 19th April 1.zip, right? This is the file which we have. It's a zip file. Okay, so if you open Topcat, right? Topcat can open zip files. So I can directly ask Topcat to open this zip file, right? So I can say file browser and I will actually go out here and where is my file? Oh God. I'll just try to look for the file and open it. You will have to open it as a FITS file. Here you should just have FITS. So you can actually L, yeah, yeah. So we have today's date, right? So like I said, it always is with the date. So this is 2025 14.9 1.zip. Okay. So I will open this over here. Okay, it's saying it has a problem. So I'm sorry. We'll go back to where the location of the file is and you right click it. If you're in Windows or whatever it is, you just open with archive utility. Okay. So if you open with archive utility, it creates a folder and inside this now you have a FITS file. Okay. So I will use this to load the table and get the FITS file. So where's my FITS file? LCO data 1. Where is this thing? We just opened it, right? 1 minute. This is it. Okay, so LCO data. Okay, so actually these are files. I need to look in folders. Okay, yeah, so here is my folder list. So it has now become a folder. So I will put LMN LCO data here. This is the one, right? 2025 419. Get into this.
Ma'am, your screen is paused.
You can't see
Ma'am,
my.
we can only see Gmail.
Oh, sorry. Then I will. Let me stop share and I will re-share. I'm sorry. Actually, I should just put entire screen. So I'll say share. Now you can see my entire screen. Now here you can see
Yes.
Topcat. This is fine, right? I'm just closing all this. So this is Topcat, right? Can you see my Topcat thing? You can see it, right?
Yes, yes.
Yeah. So now what you do is here I'm going to open the file after I opened it from the archive. So here is my file. I say file browser. This is the folder and now you'll get this. Okay. So this is E00 fits.fz. Okay. So this is my file, which is this. Okay. Fine. So here you see this is actually the problem with this is still, if you see this has a name which is 00. I'll just show it to you. Here it has E00. So E00 is the raw data. This is not yet the BANZAI data. Okay. So the BANZAI wala data is different, which will come later. And therefore, let's wait for that. Till then, I will explain something else to you, which we also need to know. Right. So I will now go into explaining that to you. What are we going to do? We are basically going to plot an HR diagram. Okay. And what is an HR diagram is what I'm going to try to explain to you. I hope you can see my entire screen, no? You can see it?
Yes.
Yeah? Okay. Right. So in astronomy, one of the most important diagrams is what is called the HR diagram. HR diagram is a very, very important diagram because if you can plot the HR diagram for a star, you can find all the parameters for a star. For example, you can find out the value of its mass, its radius, its temperature, its age. You can also assess what will be its evolutionary sequence, how is it going to evolve, and what's going to happen to this star, right? And therefore, people are actually find the HR diagram is a very important diagram, okay? Now, a star cluster is nothing but a sample of stars which actually formed from the same molecular cloud, right? Where all the stars have the same age, the same chemical composition, and the same this thing. Okay. So let me look at this. Okay. There's one more mail come from LCO. We'll look at it later. Okay. So all these stars basically form from the same molecular cloud. They have all the same distance, age, and mass, right? Now, what is interesting about these stars is that we have open clusters and globular clusters. We are studying open clusters today. And I will actually come to this thing, is that the important factor in studying stars is what is called the HR diagram, okay? So the HR diagram is nothing but a diagram of luminosity versus effective temperature, or when we do in terms of astronomy observables, it is magnitude in one filter versus the difference in magnitude of two filters, right? So that is why when we were doing our observations today, we did observations with B band filter as well as with V band filter. So here, for example, I can have B versus B minus V, right? Or I can have V versus B minus V. Even that is fine. So the y-axis has to be the magnitude in one filter, while the x-axis has to be the difference of the magnitude in two filters, right? Using this, we can plot what is called this HR diagram. Okay, now what happens is, so we have actually given our request for observations where we are trying to observe this star cluster in that, right? Now, like I told you, this is very important because if you actually plot stars in an HR diagram, here you will have a path where we have what are called main sequence stars. Stars like the sun, they will sit in a path something like this. Stars over here are called white dwarfs, which sit over here, and stars which sit over here are what are called giants. We won't go into the details of that because we don't have the time to do that. But typically, this is the HR diagram. You have luminosity over here, you have temperature over here. That means magnitude versus color. This side, the stars are large in size. This side, the stars are large in mass. This is small mass. This is large size. This is small size, right? So in this way, this is the mass. This is this thing. So if I place a star anywhere over here, I can directly tell you what is the brightness of a star. Okay. So let us go back to Topcat. Okay. So Topcat, in a way, it is like Excel. Okay. What does Excel do? It actually lets you see catalog data, right? Data which is there in a catalog, right? In a catalog form, for example, a table. Say you have a table like this. I hope you can see my Topcat screen now. You can see it. This is not coming properly because this one is basically raw data. It's not coming properly. Okay. I hope you all can see can you see my full screen? Can you
Yes,
see?
ma'am.
Yeah, great. So I think I saw one more mail coming in. Let me just see. No, it's not come in. So this is, okay, this is the one. So this is the other set of data which has come in. Let's see what is this data. This is the data of the B band filter. Okay. So you see we already got the V band filter. This is my B band filter. And here I can download the data. Okay. Only problem in this is, so I download the data which I got over here, right? Now I can go back to this. I hope you can see my screen comfortably. And I am going to, no, I'm going here. And here you can see this is 2.zip. I am going to unzip it. So this is the archive. I unzipped it. And here if you see, this is my file. Okay, this is a good file. See, you look over here. If you have E00, these are the raw data. But if you have E91, this is the BANZAI data. Okay. So let me just look at this. Okay, this one only has E00. And this one which we just now got, it has the BANZAI data. So BANZAI data is shown by 91, right? E91. So let us now open this data and have a look at it. Okay. So what I will do is this is Topcat. I'm going to go file. I will discard that table. I don't want it. And I'm now going to open the BANZAI file. Okay. So, okay, 1 minute. Let me just share this file with everyone. I'll share this file also. And okay, this is the file I'm putting my computer. And this is 2. Yeah, so this is the important file which has the extension of 91. 91 basically means that it is it's gone through the BANZAI pipeline. Okay, so that other file was not important because it did not go through the BANZAI pipeline. But this one is an important file because it has gone through the BANZAI pipeline. Now I'm going to try to just keep track of other mail which comes in of that stuff which has gone through BANZAI. Okay. Okay, so now here, this is the one that I sent you earlier is actually not of use because it is not using the BANZAI pipeline. Here I'm going to look at this one, and here I'll take LCO. This one is this, yeah. This is the second one, right, which came in 2025 419 2. And here to take this file, which I've just now given you, E91 fits.fz. Okay, this one. Now you can see, moment I opened this, I ended up with 4 files, right? Like I told you in the very beginning, the BANZAI pipeline gives me 4 resultants. You can see this is the error file. This is showing me the error in different pixels, right? Don't worry about that file. This one is the bad pixel mask, BPM, which means the bad pixel mask. This one is the catalog file. This is what we are interested in. This one is a science one. This one is the catalog file, which is the important one. So if you now in Topcat, this icon basically shows you the table data, to display table data. So click on this, and here you can see this is the table data. Okay, this is the tabular data which it's actually done. What has it done in this when it's created a catalog? For the image it got, right? It has basically found out the XY coordinates, right? And it has, these are the peak and all, don't worry, but it's given you the flux. This is into 10 power 6, that's why it's E6. So 10 power 6, it's telling you the flux of this object, which is at this coordinate, right? It's given you the flux of this object, which is 1.66 10 power 6. Similarly, here it's giving you the flux error, it's giving you this if it's this. If I want to convert this flux to a magnitude scale, I will just say new synthetic column, and I will say mag, this is B or this is V. Which one was this? I think this was B magnitude. So I'll say B. So the expression is 2.5 times log base 10 of flux. I'll take flux, right? And this will give me the B magnitude. So you can see, look over here, this, it's converted this all to B magnitude, 15.55, etc. This is the brightness in these different magnitudes, right? Which it has given me for the B magnitude data, right? This is the data for this. Now, if you remember, I even told you that this is giving me this. It actually calculates, this is doing aperture photometry. So remember I told you about the growth curve. Remember the growth curve? It would change the size of the aperture, right? You may have different brightness, right? So this is in flux in aperture 1, flux in aperture 2, aperture 1. This is in flux in aperture 3, 4, 5. So ideally speaking, like I told you, I made a slight mistake. We should actually look at the, if you remember, I showed you that you will have a peak coming and then it falls, because if I have a star and I put an aperture, if the aperture is small, brightness will be less, then it is correct, it will become up, and then if it goes outside the star, then again the flux will fall. So look at the different apertures which this source extractor has done. Source extractor has done aperture 1, which you're getting this, aperture 2, it's increased now, aperture 3, 5.48, but this is e power 5. Okay, this is, what is it? Okay, yeah, this is e power 5, aperture 3. Then you see aperture 4 is giving you 8.6. Aperture 5 is giving you 1.2 into e power 6. So aperture 5 is large. Aperture 6 is 1.2 into e power 6. So it's more than 5. And then you can see aperture 6. Aperture 6. So then probably this is the right aperture we should have used. We should have not used that aperture, but we should use aperture 6, right? Not the earlier ones, because this is the one which is peaking. We have to get the one at which it's peaking. Probably after that it started falling, so then it does not give you those readings. So you should take the one with flux upper 6. So let us recalculate it. I will put this for B. Where is B? Here, this B. And I will actually replace the column. I will say this is 2.5 times log base 10 of flux. Acha, this is, isn't this... Okay, 1 minute. If we just take flux also, 1.67 e power 6, 1.6, yeah, okay. Okay, so this is flux upper 6. So actually, yeah, so actually what we did was fine. You just take flux. It has already put all the apertures, so it's already taken flux. So that's fine. Then we are good. Then we are good. We don't need to worry about it. So now what happens is it has given me the brightness in all these different filters. Now in Topcat, you have different things. You can even do what is called a box plot, a histogram plot. If I click on this, right, I can actually, you choose the table which you want. We are in this table, and I can actually take this and make a plot of B. So you can see that how does it work? You have the peaking of the stars, which is coming till 10th magnitude, and after this you have this fall coming, right? So in astronomy, we often have a concept which is called completeness, right? That means what is the brightness with which you can actually see all the stars, right? So if, for example, you can see it like this basically means you can get it till this brightness and then it falls off. Okay. Now, I think the data has not yet come. Let me just check if there's more data come in. Okay. No, other data has not yet come in. So I hope you can see this. This is the LCO observation. This is the data archive. Okay. So you can actually look for the data which is already available for the objects, right? So for example, if we look at this, I can see this over here, and I can actually look for I can say view on archive. So this is going to show me all such data which is available on the archive, right? So you can see that this is the data which we observed today, right? Which has come up on the archive already with exposure, this and that. Like I told you, okay, this is the BANZAI V band and the BANZAI. Okay, that was only V. It's all B on. It's not yet come. The B has not yet come. Okay. So what we actually need to do is I basically need to get it in two bands, right? So what am I actually going to do? I think this would be a fun thing to do so that we continue being in touch. Okay. What am I going to do is I'm going to give this to you now as homework. Okay. So I hope you'll all manage to install Topcat, right? Everybody install Topcat? Yes. Now what am I? Okay, somebody has a problem in opening data. What is the problem? Is everybody getting the data? Has everybody got the data? I hope they have got it, right? So, yeah, right. Okay. So what am I going to show you? I'll show that to you. Now let me just show it. Okay. So we can actually look for this object. I can look for the object. I can look for NGC 2384. Okay. Pose all. Okay. So it's coming as this. This is only showing today's data. Deselect, export data, refresh data. Okay, this is still showing only today's data. Okay. So what we are going to basically do is I am going to view only science data. Okay. So what am I going to do is I'm going to give you all homework. Okay. Prerna, I think that would be good fun, right? So what I will do is, this is the data which I showed you for, this is actually not B, I think it is V filter. This is V filter only, it's not B, it's V filter, okay? We are going to send you an email, all the data for the B band as well as the V band, okay? You are going to use Topcat to open the file, okay? Once you do that, you are going to use the flux column to convert it to magnitude. So here is the V band data. Very soon the B band data will also come, and that is what we will share with you through mail, right? We'll mail you the B band data. Okay? Fine. Now once so for both of them, find out B magnitude and V magnitude. Okay? Fine. Now, once you do that, right, what you actually have to do is, if you go in Topcat, Topcat is a very nice thing. It lets you actually, there's a matchstick option, right? So this will basically match two catalogs. So I can match two catalogs. For example, here, supposing you take the B band data, you say the RA, or let me say, I'll just keep it as X and Y, okay? And you take another column, for example, I take this one. Again, I match this. Actually, this one will not do because these are not this thing files. No, these will not come. I can only self-match it. let me see if the data has come. No, it's not come. Right. So since there's been a delay in the data coming, you are going to use this thing to match the two tables. So one match table will be here. The other table will be the B band. Okay. One will be V band and one will be B band. So use this matchstick option to actually find the B band data and the V band data. Right. And let us say you actually match this. So this will match both the images of the cluster in B band as well as in V band, right? And once you do that, right, once you've done that, then you will get a common table, will be the match table, which will be the match table of both the tables. Okay. And after you do that, click on this thing. This is the plotting tool on Topcat. You click on this one, right? This is your data set. Here I'm just going to write B or V, sorry. And here instead, you should write B minus V, right? We don't have B minus V, so I'm just going to put anything, right? Supposing I've just put A, and you will get a plot like this, okay? Which will be your HR diagram, okay? So that is your homework for you to do. That is very soon as the data comes in. I was hoping that all the data comes in today itself while we are working. Maybe we should have put the request earlier. I don't know why it's only done one and not yet done the other one. But it will give you both the data. We will email you both the data sets. Like I told you, first step is find out the magnitudes, 2.5 times log base 10 of that, right? Match the two catalogs so that it's matched for the same star. And once you do that, you plot on the X, you will plot B minus V, on Y, you will plot B or V, which any of the two, and that will give you an HR diagram, which will look not exactly like this, but it may, it could actually look a little bit like this. Oops. Yeah, so I can actually, this is the Y flip. So it will look something like this, but not like this. This is not exact. This is not an HR diagram, but it will look something like this. Okay. You will get this, which basically shows the set of main sequence stars. Okay. So I think maybe that would be a fun thing to do. What do you say, Prerna? Shall we give them homework? Yeah. We can give them homework and you can try doing this. Very simple job. Moment the data comes, I will share it with Prerna and Prerna will give it to you, set it and plot the HR diagram for this cluster NGC 2384. Let me just check if I have some other data set. I can just check and see. Where is LCO data? Okay. Okay, this is a single one. I want it for 2 filters. Okay. So I'm sorry, but let me mail it to you. Moment it comes, I will mail it to, okay, this was also not there. Actually, recently I deleted all the data which I had on my laptop. Okay, that's why I've lost the data. But I will soon have it, hopefully. Okay, so I will very soon, moment the data comes in, I will share it with all of you and you will actually have the data. Yeah, so, right. And therefore your homework for today will be to plot the HR diagram. Okay. Now, in case people have an issue, they have a problem, let us wait for the data to come in. And then on some other day, Prerna, we can actually do that when the data comes in. Because problem was I actually had deleted all the real data on my system, basically to save space. I deleted all the data. Now this data is still going to come. So maybe Prerna, you have a WhatsApp group or something. Moment the data comes in, I will email it to you. Use it to plot your HR diagram. If you have a problem, we will have another session in 20 minutes. I'll show you how to do that. Okay. So we can have a 20-minute session in which we do it, or I can even record a video and Prerna, then you can share it to them and give it to them.
Um,
What would you say is good?
Ma'am, I think this will be nice idea if you can record a video and can share, because then we can make it a public live
Okay.
on
Great.
YouTube.
Great.
Will be benefited for all the participants.
Yeah, because the problem is I don't have the data. It's
No
only
problem, no problem. And we'll make a video again. And if still like problem is not justified, so then we can certainly arrange a new session, and which
yeah.
in which we can dedicate the entire session to know how to handle the data.
So I'm sure if I give the recording, I'm sure all our participants will
Yes,
manage to do
yes,
that.
yes,
I'm sure
yes.
they can do it. It won't be difficult. So we'll plot the HR diagram. I'll send you the data very soon. Moment it comes to me, I'll send it to Prerna ma'am, and you can actually. Till then, you can download Topcat, plot it, see what it looks like, play around it with a little bit, and then when the data comes, I'll share it, and you can plot your own HR diagram. Right? So we'll wind up with this. And any questions? Should I check any Prerna? Are there any questions?
So I think a lot many conversation happened in between.
Yeah,
So I request you can send your questions again. It will be easy for us to not to scroll the entire conversation, and you
yeah.
can jump into the questions directly.
And we'll email you the data files. The data files will not be
Yes,
small.
don't worry. We do have your email IDs, so we'll be sending the data.
Yeah,
And so meanwhile, ma'am will make a video, so that will be accessible for everyone.
yeah. Okay, okay, fine.
Uh,
So I hope this is fine. And please try it, check it around. And we hope to hear from you. I think it's good to give some homework also.
yeah, that is very important actually. So, ma'am, I have posted one question which is in the YouTube live. Hemant had asked, how do the photometry critically resolve the given spectral image?
No, so what happens is that if there's a specific spectral line, you know that these stars, for example, emit in, like I told you, young stars emit in H alpha, right? So, therefore, if you do photometry in the H alpha filter, you will be able to identify H alpha stars, or they are young stars. So, that is why if you center it around a spectral line, you can use it to look for a certain feature, right? For example, if there's a particular line you want to see it, you'll do it like that. So that's why it's done in that way with whatever spectrum. So there are what are called narrow band filters, which are around a spectral line. Then there are broadband filters like UBVRI. Those are just broad. They are not around a spectral line. But for example, if a star is very bright, it will have a very high brightness in ultraviolet magnitude and lesser in blue magnitude. But if it is a colder star, it will be brighter, for example, in the R magnitude and fainter in ultraviolet. So in that way, it can this thing. The photometry can actually. So in principle, if you do photometry in many filters, it could be like a low resolution spectroscopy, something like that. So
So, any other questions? So you can, in fact, you can open your mic and you can ask directly
yeah,
if you don't wish to post it. And this link which Jitendra Yadav have posted is for the your feedback,
yeah,
uh, which we expect you to share for your both the dates. One we have shared it yesterday, and this is for today's session. We'll be giving your feedback will help us to make our things more like if we need certain kind of changes we do require, so that will help us to correct ourselves. वेरी गुड सेशन प्लीज आपको ये सपोज प्लीज आप कोई ऐसा कोर्स बताएं कि फ्यूचर सो दैट इट विल इंक्रीज आवर नॉलेज प्लीज रिलीज अ कोर्स लाइक सो आई डोंट गेट the question which type of course you're asking, so any specific question you have please.
yeah. So just to let people know that somebody wrote about that, we are in the process of writing a book on all these things, and hopefully the book will be ready. Let's hope by the end of this year. Let's hope.
Okay
That
ma'am.
will help a lot of astronomy departments in the country to set up their data science courses, projects, etc.
We have another question.
Ah,
Alok,
okay,
ma'am,
yeah,
why do stars spend most of their lifetime on the main
yeah.
sequence?
So the main sequence is basically defined as the region when a star burns its hydrogen. Okay. Now stars are basically 73% hydrogen, 25% helium, right? So most of the time they are basically burning hydrogen. Okay. Now, later on in later stages, they burn helium, they burn carbon, they burn heavier elements, but those are much lesser in proportion, and therefore that phase of a star's life is much shorter. But basically, the bulk of the star is hydrogen, and hydrogen burning is main sequence. So, if you're a main sequence star, you're basically burning hydrogen, and that's the thing.
So another question we have, I think, Jitendra Yadav, ma'am, is there any other way we also can apply for data individually, like any free platform or somewhere?
Yeah, so you can actually write to the people at LCO. You can check up their website and you can write to them for data if you want to have data of any kind. And they are very nice people. There is a slew or this thing, but slew actually charges. LCO does not charge you any money. So if you request them for data, they'll give it to you without any this thing, right? But since I already have time, I can just give you a login and let you observe. So I don't mind giving people time. It's just that we can't all, 200, 300 people, we can't log in now and start observing. It will get totally confused, right? Uh, these
Uh,
things are not used to such large numbers. So if you want to do some observations, please write to me. I'll share the login to you. You can this thing. You can use my time and observe if you want.
so can we get access to the existing picture on the LECO, or also one have asked the same
What
question?
is the existing picture? I did not understand picture. The data you mean? So if you go to the LCO, I told you there's an archive portal. This is the archive, wala. This is the LCO archive, science archive. You can go to this. In this, you will actually see all the data, right? So for example, you give the object, you see, and this is basically loading all the data which is there of LC to create for. Right? I hope you can see my screen. Huh? You can see the screen. You can see the screen, no? Clear now?
Yes, yes, ma'am.
There is this archive.lco.global.
No, right now we cannot see the screen, ma'am, because it's not yet shared. We can only see you.
1 second. So I'll just, yeah. It stopped sharing. It stopped sharing. Here you can actually see, you can log in and, hold on a minute, huh? This guys. I hope you can see this. Yeah.
Yes, now
So
we
this
can
is
see.
the archive.lco.global. This is open to everyone. You can log into this. And here, for example, you can see. Okay, yeah, you have BANZAI B and BANZAI B. But this is done. Oh, it's already ready. Here it's ready. Wow. So you all have the B. Now I'll give you the. I gave you all the B. Or which one did I give you? I'll just check this. I'll take this. And here is the data. So let me down. This is downloading too. So I'll say zip download. Yeah, so you can see here is the data which is done. So I'm gonna just now itself I can share the data. Next time okay, we have almost done, but I can actually let it probably finish doing it now. I expected that's what that it will finish doing it. So you can see here. So one is B band and one is V band. I'm going to share it. So should I share it on Zoom or should I give it to you on mail?
Ma'am, either way, you can also like share it here, and individually, I can also like email to them if anyone find difficult to open it via Zoom.
Let me put this. Actually, often while we are doing it and the observations, abhi it's done. Slight difference in time, or otherwise, generally. Yeah. So here are the two band these things. One will be B band, one will be V band. Okay, you can use that and check it.
Ma'am, can you mail this also?
Yeah, I can mail it. I'll mail it this evening. I'll mail it now to you. You see, these are E91 files. E91 files means they've already gone through BANZAI pipeline. They're already BANZAI files. Bodies, oh, I should have said it. Do you have permissions now?
No.
Rina, you got permissions? Okay.
Ma'am, I received it.
Okay. Very good. So thank you very much. I think we'll wind up over here. Please have a look at the files and we can get back. Okay, whatever. I'll try to make a video and send that. Okay.
Yeah.
That's it.
I think with this, I will wrap today's session, and I'll surely be sending all the files which Priya ma'am shared to your respective email ID. Again, I would like to request kindly do fill the registration forms and do check your email IDs. It should be correct because sometimes you randomly fill and then it get bounced back. Also regarding the certificate, it will take 10 to 15 days to process things, so kindly do not bombard your emails regarding and pertaining to these things. We'll surely be giving it to everyone, each one of you, to encourage your participation in this workshop. But do give us time to manage such a huge audience in this workshop. So once again, I thank each one of you who were present in the Zoom meeting as well as who attended it from YouTube link for your active participation. And once again, we would like to wholeheartedly thanks on behalf of Planetarium and also from behalf of Prime Minister Museum and Library to Dr. Priya Hasan for her generous support in making all these information accessible to the wide range of audiences. With her generous help and support, we kind of utilize this platform to make reach of citizen science project and other related information related to space science and also astronomy. So thank you ma'am for this, and we look forward to host you offline at the planetarium so that people can get more enriching chance to interact with you.
Yeah, sure, sure. Okay.
Thank you everyone, please do write to us and do fill the registration the feedback form. Thank you so much.
Bye bye.
Bye.